Here's one more example where I'm going to use the ratio test to determine whether the series converges or diverges. And the reason I would go straight to the ratio test again is that I see the factorial there. So the way the ratio test works, we take the limit as n approaches infinity of the absolute value of, I'm going to color code this, so the n plus 1 term, a n plus 1, over the nth term, a n. So that's the limit as n approaches infinity of the absolute value. Okay, n plus 1 terms. So I make each of these n's n plus 1. So the base here becomes n plus 1. The exponent becomes n plus 1 over here in the factorial. We have n plus 1 factorial now. Okay, all of that over the nth term, which is just the given expression, n to the n over n factorial. In this example also, everything's positive, so I can drop the absolute value. So this is equal to the limit as n approaches infinity of, so n plus 1 to the n plus 1 looks like a pretty complicated expression. So I'm going to first at least write that as n plus 1 to the n times n plus 1 to the first. So that's from this expression right here, over n plus 1 factorial, which might be helpful since we know we're going to be comparing it with n factorial down here. I'm going to go ahead and take that n plus 1 factorial and start expanding it downward. So that'd be n plus 1 times n factorial for the n plus 1 factorial there. Okay. And now I'm going to multiply by the reciprocal of this fraction on the bottom. So n factorial on top, n to the n on the bottom. Okay, so see, it was nice to split these bits up in the numerator because now I've got a common factor of n plus 1 I can cancel, as well as that n factorial. And so I'm left with the limit as n approaches infinity of n plus 1 to the n over n to the n. That's what survived, which I could write as limit as n approaches infinity of n plus 1 over n raised to the n, whole thing raised to the n. Now notice this thing has the form, so it's approaching 1 inside here, 1 to the infinity, which is an indeterminate form. But what if we broke up this numerator here? So divide each part by n. So this is the limit as n approaches infinity of n over n, which is 1, plus 1 over n, raised to the n. And now hopefully that limit looks a little bit familiar to you. So it was proved back in the section with L'Hopital's rule that limits, I think the way that we showed it is the limit as n approaches infinity of 1 plus k over n raised to the n is equal to e to the k. But in any case, this is a really helpful limit to just learn to memorize. This is the definition of e to the first in this case. If you want to look at it in terms of the way we proved it back in 5.6, k is equal to 1. So this is e to the first. But yes, this right here, the limit as n approaches infinity of 1 plus 1 over n to the n is the definition of e. So if this limit here is equal to e, keep in mind, is about 2.71828, blah, blah, blah. It goes on from there. It's about 2.7, which is greater than 1. I'm sorry, I'm getting to the conclusion way in the corner here. But when the limit is bigger than 1, so since this is equal to e, which is bigger than 1, the series diverges. If the limit's bigger than 1, ratio test says the series diverges. If it's less than 1, ratio test says it converges. And if it's equal to 1, you got to try a different test. Ratio test doesn't know what to do with that. So by the ratio test, this series diverges. Because the limit of an plus 1 over an is e.